Okay. Welcome to the afternoon session of the HTTS workshop. So we're going to start the session with Ling from UIUC, who is going to talk about dynamic quorums in sleepy BFT. Take it away.
Yeah, thanks, Giuliano and Christian, for hosting this event and for the invitation. I'm not feeling my best, so pardon my voice and muffled sound from the mask. Right, so today I'd like to talk about dynamic quorums in sleepy BFT. Right, and sleepy BFT is this variant of Byzantine fault tolerance that's loosely inspired by the Bitcoin protocol. Right, and in the classic setting, when we study consensus, usually we have a fixed set of participants, and they are always there. At least the non-faulty ones are always there participating. Right, but if you think about the blockchain setting, blockchain protocols can handle a harder problem. Right? This is Bitcoin's hash rate over time. You can see it increased by orders of magnitude. Right? Some of it over the years. Right? Some of this is attributed to hardware getting better and better, but also it's also a result of more and more people tuned in and find Bitcoin relevant, and so the participation level does increase. Right. Other than that, if you zoom into a small segment, you can also find the sudden decreases in participation, right? Possibly because the price crashed, so some of the miners no longer find it profitable to mine, and so they shut down their mining operation, and this results in a drop in participation. Some of those drops are almost dropping by half, and existing, classic Byzantine fault tolerant protocols cannot handle this, right? Because think about things like PBFT. We have a fixed number of participants, right? Let's say 100, and then in order to do anything, the quorum size is 67, and you always need to find 67 votes to move forward. Right? If suddenly half of your participants leave the system and no longer active, right, then the protocol will get stuck. On the other hand, Nakamoto's longest chain consensus can handle this very well. Right? I assume everybody here knows how this protocol works. We have a random lottery, right, where one of the participants gets lucky and solves a moderately hard puzzle, and that affords that participant a right to add a new entry to the chain, right, and this keeps on going. Right, and downside of this protocol is that the latency is very high. Right? It is well known that block after appearing on the blockchain, you cannot assume it's always been there. Right? There is a chance that it's going to be reverted. Right? It's stable there only after it is buried deep in the chain. Right? But the nice thing about longest chain is that it does support dynamic participation. Right? Let's say suddenly half of the nodes, or even more than half of the nodes, disappear. Still, at some point, one of the nodes will find a solution to the puzzle, right, and the chain will keep growing. Right. Admittedly, the efficiency may take a hit because it's now going to take longer for the entire network collectively to find the next puzzle solution. Right. But eventually, we will make progress. I already mentioned this. On the other hand, the classic BFT that doesn't handle dynamic participation usually relies on what's known as quorums, right? 1/2 or 2/3 of the votes. These protocols can actually decide in 2 or 3 rounds, right? So it's a much better latency, much better efficiency, but they will get stuck right? They don't enjoy liveness if the participation is dynamic. Right, so the natural question that we want to ask in this work is, can we achieve the best of both worlds? Can we achieve dynamic participation and low latency at the same time? And the answer is yes. Right, so in a sequence of 2 papers that I wrote with Asuki Momosi and Dalia Melki, we designed 2 protocols that solve this problem. Right? It's a BFT protocol with dynamic participation and also achieves a constant latency. It is independently, a solution is given by Giuliano and Eddie Gaffney. I also want to mention that I think some of you in the audience may have heard about this talk last year. Right? So I will add a little bit of new content in the talk, right? So it's not a complete waste of your time. All right. So let's now define the formal model for dynamic participation. Right? We have a set of big N potential participants who can participate, right? And they know each other, and we have a PKI, so everybody knows everybody's public keys. For now, we will assume the set is fixed, right? Meaning that there's no stake changing hands or no membership changes. The protocol should be fine, should be able to be extended to a changing set, right? But we didn't work out the details, so I don't want to claim anything there. And the problem we're going to solve is what's known as atomic broadcast. Right? Participants propose values and they agree on the ledger. Now, the key assumption, the key difference in dynamic participation from static one is that at any time t, there is a small n sub t participants that are active. Right? This small nt can be anywhere from, let's say, 0 to t, 1 to n. And among those who are active, we say half of them, we assume at most half of them are adversarial. Right? So this corresponds to the honest majority assumption. Okay. Now, an honest participant can transition between active and inactive at any time, and it does so in the adversary's control, right, without any advance notice. Right? So this is a very hard model, right, where the adversary can put some nodes to sleep and then wake them up later at will. Whereas an adversarial participant can go from inactive to active. Right? So an adversarial node can be sleeping in the beginning and can wake up some point during the protocol. Right? However, there's a modeling difficulty. We don't know how to model an adversarial participant going from active to inactive, right? Because these are Byzantine nodes. Once they wake up, they can give up their secret key to another adversarial node, right? And then when they goes back to sleep, it's as if they never left, right? Another minion controlled by the same adversary can still participate on the behalf of that other adversarial participant that went offline, right? So this is a kind of artifact in the model. We can only handle, we can only consider adversarial participants with the increasing participation level, right? But I will say that the protocol looks okay, even if the adversary truly leaves, truly goes down. Right? We just don't know how to analyze that in a rigorous fashion. Okay, and this is something new in this talk versus what I talked about a year ago. Previously, most of the dynamic participation protocols, they assume the adversary participation is fixed. Right? It never increases, it never decreases. That's the case in many of the proof of stake longest chain protocols. Okay, so lastly, the assumption on timing model. We assume there is a known message delay bound between honest and active participants. Right? So this corresponds to the standard synchrony model. Right? And there is it is not hard to see that if we assume asynchrony or partial synchrony, then this sleepy dynamic participation BFT is impossible to solve. Okay, now let's look at the techniques that we're going to use to solve this problem. I'll start from the classic static quorum systems that classic protocols use. The idea here is that the classic protocols, they always proceed if they collect a fixed threshold number of messages or votes in one step, right? Then they will move on to the next step. Right? So what is this threshold? In the synchrony case with honest majority, this threshold is usually half, right? or more than half. Right? So concretely, if we have 6 participants, then we require 4 votes to form a quorum, right? And 3 is not enough. Okay, but in the dynamic participation model, right, we don't have this notion of predetermined threshold, right? The threshold needs to be based on the actual participation level, right? However, nobody knows the actual participation level, right? Nobody has this global view who is online, who is not, right? So the best we can do is to base it on the perceived participation level, right? So basically, we'll ask everybody to announce they're there, right? Then I'll count how many announcements I got, right? That will be my perceived participation level, call it small n, and then we'll set the quorum threshold to half of that. But okay, so in this case, if 3 of them are participating, right, they all send I am awake messages, then everybody will perceive a participation level of 3, and then the quorum size would be 2. But that brings the challenge. Right? The challenge is that malicious nodes, Byzantine nodes, may not announce themselves honestly. Right? They may announce themselves in a partial fashion. Right? So I send I am awake to Giuliano, but I don't send that message to Kristen. Right? So that will result in these 2 nodes, A and B, have to perceive different levels of participation. Right? That creates a problem because now they will have different thresholds for their quorums. Right? And the result of that is that now a quorum certificate, right, a set of votes that form a quorum, is no longer transferable. Right? By that, I mean, let's say we have 5 votes here. For this green node, right, suppose this node B perceive a participation level of 9, right? Node B will believe that these 5 votes form a quorum, right? But node A, the orange one, it perceives a participation level of 11, right? So it will not consider 5 votes sufficient, right? So this is what I mean by quorum certificates being no longer transferable. Right? And this is a pretty big problem in for classic protocols, right? So a very common step in classic BFT is as follows. Right? So if one honest node, right, makes a move, right, then every honest node weakly support that move. Right, so this is such a prevalent step in classic protocols that we don't even think about it. For example, if one node decide, then usually we want all the nodes to lock on a certain value to protect that the safety of that value. If one node locks, we want everybody to have seen that proposal, to ensure liveness usually. And or if one node casts around 2 votes, then everybody should have received round 1 votes, so on and so forth. There are many steps in classic BFT that has this flavor. And usually, this is pretty easy to achieve. How? Because if one node received a quorum of votes, it's going to make that move. All it needs to do is to forward the quorum of votes to everybody else. Excuse me. So everybody else will receive that quorum of votes. They will also recognize that is indeed a certificate, right? So you received it in time, so you make your strong move. I didn't receive it in time. I received a little bit late, forwarded by you. So I'm only going to weakly support that move, right, as opposed to making the move myself. And another way to categorize this is using graded agreement. If one node output some value with grade 1, then we want everybody else to output with grade 0. Okay, so the key step in dynamic participation BFT is to restore this notion of transferability. And we're going to use technique called time-shifted quorums. Okay, so here I'm just going to first present the protocol, dump the entire protocol on you. So sorry about that. And then we will see some intuition. Right, so round 1, everybody send a pre-vote for a value and also send a wake message announcing that I am here. Now round 2, everybody count the number of pre-vote messages, and let's call that V1. Okay, also they're going to forward all the messages they receive, right? So vote round 2, even though I didn't write sending any message, they should send all the pre-vote and awake 1 messages they received from the last round. Okay, so next round, they will count again the number of pre-votes they received by now, right? And let's call that V2. Right? V2 is at least as large as V1, right? Because you are counting again. Everything you counted in V1 is still counted in V2. Okay, so they're also going to count the number of awake 1 messages and store that in M2. And they're going to send awake 2. And then if V2 is greater than half of M2, and they're going to send a vote. Now last round, they'll count 1 more time, the awake 1 messages, they store that in a variable M3. And if V1 is greater than M3 over 2, then make that move. So why is this right? Why does this restore the transferability? Right, let's to see that, let's bring in another node. Right, so we want to argue that if one node, let's see which order do I have it here. Okay, yeah, I think if the bottom node makes a move here, we want to argue that everybody will vote, right? Therefore, everybody will see enough votes greater than awake 2, so they will weakly support that move. Right, right, here's how it goes. Right, so we can first argue that V1 of anybody is no greater than V2 of any other node. Right? Why? Because this bottom node count V1 is going to forward everything counted in its V1, right, to everybody else. Right? So that other node, when it counts V2, it will at least count everything that the bottom node has counted. Right. So V2 of anybody will be at least as large as V1 of this bottom node. Okay, so for the same argument, we can claim M2 is no larger than M3. Right? For the exact same reason, right? If somebody counted M2, it is going to forward all of those things counted in M2 to the next round. Right? So everybody will count at least as large or larger M3. Right? That's pretty much it. Right? So since we have these two inequalities, right? So if one node sees V1 is greater than M3 over 2, V1 is greater than half of M3, then that everybody else will see V2 is greater than half of M2. Because this V2 is larger than V1, and this M2 is smaller than this M3. Right? So therefore, if this one holds, right, this V1 greater than half of M3 holds, then V2 greater than half of M2 will also hold. Okay, and right, therefore, if every one node makes a move, then every awake honest node voted, right, and that will be large enough for a quorum, right, that will exceed half of everybody's perceived participation. Okay, so this is the protocol we designed in the CCS22 paper. It left a few unsatisfactory properties of the protocol. Right, the first one is that while safety holds, regardless of in the presence of arbitrary fluctuation, right, liveness does require a period of stable honest participation. Right. Why is that? It's because in this protocol, in order for me to proceed to the next step, right, to make this move, I need to compare two variables, V1 and M3. Right, M3 is the thing I counted in this last round. Right, V1 is something I counted 2 rounds ago. Right, so in order to do this, carry out this step, I have to be around, right, for these 3 rounds in a row, right? In order for me to have a V1, have an M3, and do this comparison. Right? So that's why it requires a period of stable participation. Right? And second, the adversarial participation in that previous protocol must be fixed throughout, right? Just like every prior work there is. And lastly, the latency is a constant, but is a pretty large constant. Right? Requires at least 16 rounds. Right? So in a follow-up work this year, we solved some of these problems. The first one is this stable participation that somebody needs to be around for, right, to count V1 and to count M3. Right? The solution is actually pretty simple. Right? We just need to add a step where everybody is going to send the V1 they counted. Right? And then in this last round, a node receive a bunch of V1 reported by others, right? Then just use the median V1 among them. Right? So because we have honest majority, that median will be sandwiched, will either be honest nodes reported V1, right, or will be sandwiched within 2 honest nodes. Right? So this gets rid of the stable participation requirement. Second, we can now allow growing adversary. All right, so why is the previous protocol not allowing growing adversary? It's because the arguments we used is that everybody votes. Right? If everybody votes, then everybody will see enough votes, right, that exceed the half of their participation, right? But if the adversary starts growing, right, they can inflate the total number participation, right? So back then, the participation was 50 and we got 30 votes. So that is a quorum. But a year later, now the system got much more popular. Like, there are thousands of nodes and hundreds of adversary. Right? So these adversaries can pretend that they were always there, right? Send the awake messages, right? And that transferable quorum certificate is once again no longer transferable. And the solution to this is also relatively simple. We're going to so we just need to use a BFT protocol that does not look too far back. Right? So some of the protocols we used, we kind of modified from hot stuff. Right, so that protocol needs to look very far back. Right? If there is a quorum certificate from like 100 views before, that still has an influence to the current view. Right? Instead, we can customize a protocol where nodes actions in the current view only depends on what happened in the previous view. Right? Intuitively, it just means if you don't have a certificate to input, right? Okay. So intuitively, it means we are constantly updating the certificate, right? If we have an old certificate, then we're going to vote for whatever value in that certificate, right? So to bring it to a newer timestamp, right? So that we can forget about the old one. Yeah, and lastly, it's latency reduction. It's once again, most of the improvements come from a more customized protocol that to build off of. Right? Hot stuff is a partially synchronous protocol. I think in hindsight, we should not have started from that one. If we started from a synchronous protocol that decide first and then handle the locks, we'll have a more efficient one. All right. So yeah, so that's to quickly summarize. I think this notion of time shifted quorum is pretty interesting. Right? We used it to solve quorums in a dynamic thresholds, right? Which in turn helps us solve BFT consensus under dynamic participation. But I hope it has other use cases, potentially in the heterogeneous trust model. And yeah, thank you.
Any questions? Yes, you have a mic there.
Yeah, so you mentioned about looking back, not much into the past, but most of the protocols that use the leader-based approach with views and like Paxos-based protocols, they can progress through a very long sequence of unsuccessful views. Yeah. So you define past. So how do you define the past more precisely?
Yeah, it's the yeah, like you said, it's we don't want unsuccessful views. Right? Indeed, Paxos PBFT have that behavior, but because it's they want to handle partial synchrony, right? Right. So in this case, we're in synchrony anyway. So if everybody votes, everybody will receive the votes. So we can always get a captured up-to-date situation in the system.
So I got it wrong because it meant hot stuff, but this is the synchronous hot stuff.
Yeah, we were mimicking partially synchronous hot stuff, right? Which in hindsight is not the right decision.
So I have a quick question. So would you say that if I take any protocol and let's say it looks back 3 rounds, then necessarily this means I need stable participation for 3 rounds, for a moving window of 3 rounds, or
I think maybe it's not that simple, because looking back from the entire protocol's perspective is fine, right? So by that I mean, if my action depends on a quorum that's generated 100 views ago, right? But that certificate may not be generated by me, right? Or may not have my contribution, right? So it doesn't necessarily require stable participation. Right? The first protocol I showed requires me to compare 2 variables I set in this round and 3 rounds ago. Right? That is where it needs the stable participation assumption.
I see. Okay. Okay, let's thank the speaker again.